Hey folks, in 8C we're going to talk about real population growth. So what we know from the beginning of this unit is that while populations do tend to grow exponentially at first, the parable of the bacteria in the bottle teaches us that exponential growth is not sustainable over time. So we're going to talk about what real population growth models tend to look like. Okay, the average annual growth rate for world population since 1650 has been about 0.7%. However, the annual rate has varied significantly. It peaked at about 2.1% during the 1960s and is currently, or as of the last decade, about 1.1%. So what we're going to do is find the approximate doubling time for each of these growth rates, and then we'll use each doubling time to predict world population in 2050 based on 2013's population of 7.1 billion. Okay, so we are going to need a few of the formulas from section 8B, so I'll remind you of what those are. So the first formula that we're going to use is going to be our approximate doubling time formula. Oops. And remember that that was the doubling time is approximately equal to 70 over P, where P is the percentage growth rate. So let's do these for the three growth rates that we have. So for 0.7%, our T double would be about 70 over 0.7, which is 100 years. Okay, so for the 2.1%, our doubling time is going to be 70 over 2.1, which is about 33 years if we throw that in the calculator. Okay, and then let's do from the most recent, so for 1.1%, our doubling time is 70 divided by 1.1, or about 64 years. So now we're going to use the other formula from 8B, which is new value equals initial value times 2 to the T over T double. All right, so let's see, 2050 is 30 years from now. And let's assume we have a population of about 7.1 billion. We're actually close. We'll go with 8 billion as of now. So for the 0.7% annual rate, the 2050 pop is going to look like this. We're going to do 8 billion times 2 to the 30th over 100. So the 30 represents how many years from now till 2050, and the 100 is our doubling time. So let's go ahead and pop this in the calculator. We're going to have 8, just remember we're in billions, times 2 to the power of 30 over 100. So that comes out to about 9.8 billion. All right, so now let's do the other two. So for 2.1%, our 2050 pop is going to be the same 8 billion times 2 to the 30 over, now I'm going to use the doubling time of 33 years. So with that one, we get a much larger, about 15 billion. And finally, we'll do the, for 1.1%, 2050 pop is 8 billion times 2 to the 30 over 64. And so that's 11 billion. So we see drastically different results with seemingly small changes in the annual rate. All right, so let's talk about some rates. People aren't just populating, right? They also die off. So we call the overall growth rate the birth rate minus the death rate. And for any particular species in a given environment, we call the carrying capacity the maximum sustainable population. So that's the largest population that the environment can support for an extended amount of time. So example 2, in 1950 the birth rate was 37 births per 1,000 people and the world death rate was 19 deaths per 1,000 people. By 1975 the birth rate had fallen to 28 births per 1,000 and the death rate to 11 deaths per 1,000. Contrast the overall growth rates in 1950 and 1975. All right, so let's look at 1950. We're going to have births, let's see, 37 births per 1,000 people. So that's my birth rate minus my death rate is 19 per 1,000. So this is going to leave my growth rate at, let's see, 18 out of 1,000. Which is a 1.8% overall growth rate. All right, and let's contrast that to 1975. The birth rate had fallen to 28 births per 1,000 people. The death rate had also declined to 11 deaths per 1,000 people. Which is going to give us 17 out of 1,000, or 1.7% overall growth rate. So even though births had declined, deaths had also declined, so it didn't change the overall growth rate by much. Okay, moving on. So, as we said, we can't have exponential growth forever. It's not sustainable. So what happens in reality is something called logistic growth. You might have discussed this in environmental science. So when the population is small relative to carrying capacity, logistic growth is exponential with a fractional growth rate close to the base growth rate R. As the population approaches the carrying capacity, the logistic growth rate approaches 0. The fractional logistic growth rate at any particular time depends on the population at the time, the carrying capacity, and the base growth rate R. So this is kind of our logistic model, and the idea is that the logistic growth rate will be constantly changing depending on the population. As the population gets close to the carrying capacity, this fraction is going to get close to 1. So once the population is the carrying capacity, what you'll have in that set of parentheses is just 1 minus 1, or 0, and the logistic growth rate stabilizes. It settles at 0. There is no growth. So that's the case where the births and the deaths are the exact same per 1,000 people. So here's what this model looks like. An exponential model is in blue, and you can see that the logistic growth model matches that early on in the timeline. But as the population increases towards the carrying capacity, a logistic growth model will naturally taper off towards that carrying capacity. Whereas you can see an exponential model would breach the carrying capacity, which can become a huge issue for the environment. Oops. All right. Let's go over one more example. So it says the global population growth rate has been slowing since around 1960, when the growth rate was about 2.1%, and the population was about 3 billion. Assume that these growth rate and population values represent one point in time on a logistic growth curve with a carrying capacity of 12 billion. Does this model successfully predict the 2013 growth rate of 1.1%? Given the 2013 population of 7.1 billion? Explain. So, what we're going to do is use that logistic model, which is the logistic growth rate equals the base growth rate times 1 minus the population divided by the carrying capacity. So we're going to have to make some assumptions, and one of the assumptions we're making is that the carrying capacity is 12 billion, And the first thing we need to solve for is the base growth rate for 1960. And so what I'm going to do is isolate R by dividing over everything else. So R equals my logistic growth rate divided by 1 minus the pop over, sometimes we call the carrying capacity, K for short. Okay. So I'm going to come up with a base growth rate for 1960. So I'm going to use the values that they give us from 1960. So R equals, they say the growth rate in 1960 was about 2.1%. So that's what I'm going to use as my logistic growth rate. So 0.021 as a fraction over 1 minus the population in 1960 was 3 billion, divided, we're assuming carrying capacity to be 12 billion. Okay, so we can put all that in the calculator and we get about 2.8%. So now let's solve for the 2013 growth rate using that as our base. So 2013 logistic growth rate will be our base 0.028 times 1 minus, we want to use our current population, which is 7.1 billion, and we're assuming the carrying capacity still to be 12 billion. When you multiply this out, you actually end up with about 0.011, which is 1.1%. So if we are on a logistic growth model, yes, this model does correctly predict what our 2013 logistic growth rate was. If population growth continues to follow this logistic pattern, then the growth rate will continue to decline and gradually level out at about 12 billion. Here's the thing, human population has not been following logistic growth over longer periods. The base growth rate we found in our logistic model of that 2.8% implies that the actual population growth rate should have started long ago and gradually declined to 2.1% by 1960. The 1960 growth rate was an all-time peak, and while we see evidence that the population has followed a logistic trend since about 1960, it hasn't followed this trend over a larger period. So it's still too soon to conclude that the logistic trend will continue in the future. And you can see in nature that even though we assume populations have a carrying capacity based on their environment, you can have things happen where a population overshoots its carrying capacity and then kind of Mother Nature takes course and you see a collapse in the population of the species that we're talking about. So this is a phenomenon known as overshoot and collapse. And the hard thing about this is we made a big assumption that the global carrying capacity for humans is 12 billion, because it actually depends on many different things like consumption of resources, and different countries consume at different rates, and also about the environmental impact of the average person. Technology can also change carrying capacity. Like long ago, we didn't have the ability to live in a desert until we figured out how to move water through the desert via canals and modern plumbing. Now we have the ability to live in the desert. So things like that can all change the carrying capacity. So whenever we make assumptions about our population model, those assumptions, the predictions are only as good as the assumptions that they're based on. So you can see one case study of population of Egypt over time does not look at all like a logistic curve in the long run, right? We see a little bit more of a stable population model in more modern times, but all sorts of things come in to play in population models that we can't predict, like plagues, the Black Death, and overthrow of governments, things like that. All right, folks.